All right, I realized I forgot to tell you what these numbers mean, so that might be helpful. The number on the left is what player A gets if that is chosen by both of them, and the right is what player B gets. So if player A gets up and chooses up and player B chooses left, player A gets 10, player B gets 20. Okay, so there are different strategies. One is a dominant strategy. This does not happen all the time. So this is a strategy that results in the highest payoff to a player regardless of the opponent's action, like it's just the best. So if we think about player A, if player B chooses left, player A, the options are 10 and minus 10. If player A chooses up, it's either going to get 10 or 15. If player A chooses down, it's either going to get minus 10 or 10. So clearly choosing up is a dominant strategy. Now what should player B do? What it's probably going to do is realize that player A is going to choose up. So it's like we usually assume perfect information or something like that in these cases. They know what the options are for the other ones. So it's going to say, well, player A is definitely going to choose up. So I can either choose left or right. I'm going to choose left. So this, up and left, is what we refer to as a Nash equilibrium. So a secure strategy, and which is something I didn't talk about, is a strategy that guarantees the highest payoff given the worst possible scenario. Sometimes I like to think like this. Worst case scenario, I'll still be okay, right? So for player B, let's think about this. If it chooses left, it's either going to get 20 or 7. If it chooses right, it's going to get 8 or 10. So it might think, well, what's the worst case scenario for me? And the worst case scenario is, let's see here. Yeah, the player A chooses down. I get very confused about this. Let's see what it says. We'll go back to the Nash equilibrium because that's the one that matters. This is a condition describing a set of strategies in which no player can improve her payoff by unilaterally changing her own strategy given the other player's strategies. So no one can make themselves better off. So that's what's referred to as a Nash equilibrium. Let's go back to that because that's actually more important. All right, so the player A has a dominant strategy up. Player B has no dominant strategy. Player A's secure strategy is up. It guarantees at least a $10 payoff. Player B's secure strategy is right because it guarantees at least an $8 payoff. Yeah, I could see that. So worst case scenario, it would choose an 8. Whatever, I'm not going to ask you about secure strategy. Nash equilibrium is the important one. So a Nash equilibrium results when player A plays up and player B plays left. Again, player B is going to recognize that player A has a dominant choice, dominant strategy, and then it's going to say, well, then I'm going to choose left. Okay. So your textbook actually has this interesting Inside Business 10-1 that I recommend reading. So I remember the movie A Beautiful Mind when that came out. It says it was 2002. I must have watched it later. So I think I was in grad school when I watched it. So it's about this guy, John Nash, who won the Nobel Prize in 1994 for his work on game theory, and a Nash equilibrium is based on him. And there's a scene in the movie where they're at a bar. So him and his friends are at a bar, and there's like a table full of women, and they want to ask the women to dance. And like the worst stereotype ever, there's a beautiful blonde woman and a bunch of brunettes. And they all want to dance with the blonde woman. So they're about to go ask her to dance. And John Nash, according to the book, in the movie says, oh, wait a second, what's going to happen is she's going to turn us all down and then we'll try and dance with her friends and they're going to say no because no one wants to be second best. So it's better if we all just go for the brunettes. And according to the book, again, there's this image of like all the men dancing with the brunettes and the beautiful blonde sitting there alone. And apparently in the movie, he goes home and writes his paper on Nash equilibrium. It's really interesting, though, because I remember watching this in grad school and thinking, wait, does that make sense? And it doesn't, because that's not a Nash equilibrium. So what a Nash equilibrium would be is no one can make themselves better off. in that circumstance, someone could dance with the blonde woman and make themselves better off. So that's not a Nash equilibrium. Found that very interesting. Anyway, moving on. So I have to be honest with you. I was looking at this earlier. I was recording this lecture, and I got real confused on this one. So let's say there's a pricing decision, firm A, firm B, and I think of these as gas stations on either side of the road. They can either charge a low price or a high price, and how well they do depends on how well the other does. So I got confused because I was thinking of a dominant strategy, and I was like, okay, for firm A, if firm B chooses a low price, it's going to get, or if it chooses a low price, it's either going to get 0 or 50. And if it chooses a high price, it's going to get minus 10 and 10. And I thought, oh, there's a dominant strategy of a low price. And I did this whole thing. I'm talking to you guys, and then I pull up the answer, and I'm like, oh, that's not right. That's not a dominant strategy. That was my problem. Because 0 and 50 is not better than negative 10 and 10, right? There's no dominant strategy in this case. So what's going to happen is you have to think it through a little bit more. So think, okay, if we are both charging a high price, so I'm firm A, we're both charging a high price, would firm B have an incentive to lower their price? Yes, they would, because they get $50 in that case, or $50 here in that case. Would firm A have an incentive to lower their price? Yes, they would, because they would get $50 in that case. So this 10 and 10 is not a Nash equilibrium because people would have an incentive to change. The Nash equilibrium is 0, 0. So that's why I was confused. Hopefully me sharing that helps you guys out. So this is an interesting scenario because it makes both people worse off. And if you've ever taught the prisoner's dilemma, which I think one of you has done, I think maybe it was Rachel, it's very similar because you've got the inferior outcome, I think, is the one that you choose. But the payoffs associated with the Nash equilibrium is inferior from the firm's viewpoint. If they could agree to both charge the high price, they would both be better off. So why do they not do that? Number one, it's illegal. That's collusion. It's happened before. I was just teaching my class. I teach the economics of art sometimes. And there was a big collusion scandal between Sotheby's and Christie's, the big auction houses, back in the early 2000s. It's illegal. You can't do that. And maybe more importantly, both would have an incentive to cheat. That's what we would call an unstable equilibrium. So what happens is firm A has an incentive to cheat, and firm B also has an incentive to cheat. All right, the book also goes through this example of advertising and not advertising. So if you want to pause and try and think about the answer here, actually I'll do the same. All right, so I just paused this and my colleague Sadafka Beck stopped by and she's like, how's it going? And I was like, oh my God, I am really struggling through game theory. I love this stuff, but man, it's hard. I got to get in the right mindset. So I don't know if you guys were able to determine. Neither firm has a dominant strategy. And what's going to happen is the Nash equilibrium is going to be that they both advertise. You might want to take a look at the book because the book explains why it's listed as low price and high price. But basically what's going to happen is if this is a one-shot game, they both would be better off again by choosing this option, but both of them would have an incentive to cheat if they chose that option. So it's not a stable equilibrium. So collusion would not work because this is a one-shot game. If you and your rival agreed to not advertise, each of you would have an incentive to cheat on the agreement. Okay, so that's the deal with that. I think I have one more example here and then we'll cut it off. We'll either pick it up next week or we'll just move on and say that's enough game theory. There's instances where you want to coordinate. And so if you think about different firms choosing the types of outlets to use, this reminds me of something called network externalities, which is like everyone has to decide to use like you know how in the rest of the world people use WhatsApp? It's this thing that Facebook actually bought up. It's like a texting thing. Like if I was the only one who decided to do that, like that would be silly because none of my friends do it. It's like an all or nothing thing. So it's kind of like that with coordination. So you can either have two outcomes where you both use 120-volt outlets or 90-volt outlets. It's the same outcome, but you don't want to, if the other one doesn't agree with you, you both lose. So in this case, there's two Nash equilibriums associated with this game. I refer to this as multiple equilibria. And basically, you have to be able to coordinate. Like, that's the thing we learn from this, is either have a government set a standard or permit player communication. This is something that, so I'm a development economist, this is something that's common in like modern day development models. So you can have a multiple equilibria situation. So for example, you can have firms that need high skills and high skilled workers, firms that don't need high skills and low skilled workers. And both of those would be a stable equilibrium. And so it's just like a matter of coordinating. So that's something I'm familiar with, is multiple equilibria. And actually multiple equilibria is something that's more likely to occur in developing countries. So this is where I'm leaving it. This is not easy stuff, okay? But it's fun stuff. I can imagine you guys being able to set up some sort of experiment. Some of you might already do this with the prisoner's dilemma. It's a way to reach out to math students that really like math, because it's upper level math, right? Game theory is an upper level math course. And, but it's hard. So on the homework this week, what I've done is I've given you 3 attempts, just because this is probably something that we need a little bit more time on.